talking about the normal distribution. So students will be able to draw and label a normal curve and use it to answer questions. And we'll be able to use the 68, 95, 99.7 rule, which is also called the empirical rule, to tell if a set of data is normally distributed. Okay, so let's first talk about a symmetric distribution. So there are different types of distributions. You can have a negatively skewed distribution, symmetric distribution, or positively skewed distribution. I'm just going to focus mainly on this one, just because that is essentially what a normal curve is. So a symmetric distribution, so symmetric, remember, means the same on both sides. This is what a symmetric distribution is going to look like. The mean and the median are going to be approximately equal, and the data is evenly distributed on both sides of the mean. So our focus today is about a normal distribution. So this right here is what a normal distribution looks like. So this visual is just showing us like our sample size. If our sample size is 100, 10,000, and then the population is actually going to be a smooth curve. So the normal distribution is a continuous, symmetric, bell-shaped distribution of a random variable. Okay, so I would write this down. It is the most common continuous probability distribution, and so it occurs the most often in normal distribution. And so that's why we are learning about it today, and there are some special rules with that. So again, the graph of the curve is continuous, bell-shaped, and symmetric with respect to the mean. I would definitely write that down. The mean, median, and mode are equal and located at the center. Okay, we'll draw this in a second, but I would write down this bullet point. The curve approaches but never touches the x-axis. And then I would also write this down, that the total area under the curve is equal to 1 or 100%. So you'd have 100% of the area underneath the curve. Okay, so the area under the normal curve represents the amount of data within a certain interval, or the probability that a random data value falls within the interval. The empirical rule, which is also referred to sometimes as the 68, 95, 99.7 rule, can be used to determine the area under the normal curve at specific intervals. Okay, so definitely draw this. This is our normal distribution. This is really important for the normal curve and some of the rules with it. So it says in a normal distribution with mean, and then this symbol mu, that's the symbol we use for mean, and that is shown right here. So this in the center of my graph is my mean, and standard deviation, sigma. This is our symbol for standard deviation. Okay, so if we look at our graph, so go ahead and draw a graph, draw this normal curve. Okay, it's always going to be this bell-shaped curve. The mean is always right here in the middle. So right here in the middle, this symbol, remember, means it's the mean. Okay, so this next bullet point says 68% of the data falls within one standard deviation of the mean. So if I go, so this is saying mu plus one standard deviation, so mean plus one standard deviation. So think about this is one, let me write that underneath. In either direction, this is one standard deviation away. So if I go one standard deviation away, that is going to be 35% of my data on either side. So 68% of my data is one standard deviation away from the mean in either direction. Then, if I go two standard deviations away, this section between one standard deviation and two standard deviations represents 13.5% of my data. And same thing over here, if I go two standard deviations less than the mean. Overall, that represents 95% of the data. So if I'm two standard deviations on either direction of my mean, that represents 95% of my data. So 68, 95, and then 99.7. So now if I go three standard deviations away in either direction, that's 2.35% on each side. And so that represents 99.7% of our data. Okay, so if you remember what I said before, that technically that there is 100% of the data under the curve. That means there is a little bit on each tail end. So on each tail end, really we have, let me just point to this, there is 0.15%. So on each tail here, we have 0.15%. Okay, but 68% of the data falls within 68%, one standard deviation of the mean. 95% of the data falls within 2 standard deviations of the mean, and 99.7% of the data falls within 3 standard deviations of the mean. So let's look at an example of this. This says the hourly wages of 2,400 construction workers are normally distributed with a mean of $36 per hour and a standard deviation of $12 per hour. So problems we look at are going to give us the mean and the standard deviation. And it tells us that it's normally distributed. Okay, so we know that we're going to have a normal curve. So this right here is already set up for us. The 36 is our mean. And then it tells us that the standard deviation is $12 per hour. So one standard deviation away, we added 12 to that, and then one standard deviation less than, we subtracted 12. So this is one standard deviation away, and then add another 12, that would be 2 standard deviations away. So you're just using the information given to us here. Okay, so it says about how many construction workers earn between $24 per hour and $48 per hour. So we are looking at, let me get rid of this. We are looking between $24 and $48 per hour. So we're looking at this section of the data. Well, if we look at this empirical rule, the 68, 95, 99.7 rule, that told us that one standard deviation from the mean is 34% of my data. So this is 34% and this is 34%. Okay, so that is 68% of our data. Okay, so between $24 and $48 per hour, we're talking about 68% of our data. Up here, it tells us that we had 2,400 construction workers. So we're just going to do 2,400 times 68%, which is 0.68. And if we do that in our calculator, we get 1,632. So about 1,632 construction workers earn between $24 per hour and $48 per hour. And we know that just because it tells us that this is normally distributed. So we're using a normal curve, and we're using that 68, 95, 99.7 rule. Okay, let's look at another example where we actually have to draw our normal curve. So it says the heights of 1,800 adults are normally distributed. So that is key, the fact that it's normally distributed, with a mean of 70 inches and a standard deviation of 2 inches. Draw and label a normal curve. Okay, so let's do that first. Let's see how this curve looks if I draw this. My curve is probably not going to be very good drawing with this. Okay, so draw a bell curve. Try to make it as symmetric as possible. Not too bad. Okay, it tells us that we have a mean of 70 inches. So my mean is going to be right here in the middle. So I'm going to fill in that is my mean right at 70. Now, it tells us that we have a standard deviation of 2 inches. So I'm going to go a single standard deviation away, and that's going to be plus 2 inches. So I'd be at 72. Then I'm going to go another standard deviation away, less than. So I'm at 68. So this represents one standard deviation away. So this would be 34% of my data here and 34% of my data here. Okay, then I'm going to go another standard deviation away. So my standard deviation is 2 inches. So I'm going to add another 2 to that. So I'd be at 74. And I'm going to go below as well. And so then I'd be at 66. Okay, this right here represents 13.5% of my data and 13.5% of my data. Okay, then we need to go another 2 standard deviations away. Or sorry, another single standard deviation away, so add 2 to it, so 76. And then right here, we'd be at 64. And then this represents 2.35% of my data. Okay, so 1 standard deviation away, 2, 3 standard deviations away. This is our drawing and labeling our normal curve. First question says, what percent of adults are between 66 and 74 inches? So we're looking between 66 and 74 inches. So we're looking at this distance here, okay? So that is 2 standard deviations away from the mean. And if we look back at our rule, if we're 2 standard deviations away from the mean, that is going to be 95% of our adults, okay? We could also just add these up. Okay, so you do need to know like what percentages we fill in. So we would just add these up and get 95%. Then the follow-up question says, about how many adults is that? So we had 1,800 adults. And we would take 95% of that, so times 0.95. And that is going to give us 1,710 adults. Okay. We might actually skip this problem. You can try this on your own if you want to. Say very similar. So it's normally distributed. It gives us the mean. It gives us the standard deviation. Asks very similar questions. Okay, one more that I want to talk about is if you're given data and telling if it's approximately normal or not. So it says below is data on the number of votes out of 538 that each state and DC gets in our electoral college, Senate, and House of Representatives. The mean of these 51 data points is 10.55. So our mean is 10.55, and the standard deviation is 9.48. Could this data set be approximately normal? Explain your answer using both the graph and the 68, 95, 99.7 rule. So first of all, this is a stem and leaf plot. So the way you read this is like this is the first set of numbers. So 0, 3. So this would be 3, 3, 3, 4s. These are 5, 6, 7, 8, 9. Then this is the first part of the number. So this would read 10, and then 11, 12, 13, 15, 17, 20, 21, 27, 31, 34, 55. It even has, like, a lot of times they have a key. So, like, 1, 5 is a state with 15 electoral votes. Okay. When it says use the graph, like, this is sort of, look at this graph, like, these data points. So this is the benefit of a stem and leaf plot. Is we can see, like, this does not look like it's normally distributed. There is not, like, this is the high point here, and there's not about the same number of values less than and above it. Like, think about if you drew in a curve through this is skewed one direction. It does not look like it's symmetric, okay? So we can kind of look at it and say, this probably is not normally distributed, but let's also talk about the 68, 95, 99.7 rule. So if I know that our mean, and I'm not even going to draw a full curve, I'm just going to draw my line. Let's see if I can draw a better line than that to help us visualize this. So if my mean, there we go, is at 10.55, and we know one standard deviation away is 9.48. So if I add 9.48 to that, I would be at 20.03, and that should represent 34% of our data. And then if I subtract a standard deviation, so if I subtract 9.48, we should be at 1.07, and that should represent 34% of my data if it is normal. Okay, so if it is normal, that's what it should represent. So let's just check one standard deviation away. So one standard deviation away would be all numbers between 1.07 to 20.03. And that if it is normal, that should represent 68% of my data. Well, let's see if that's the case. So I counted up how many numbers were between 1.07 and 20.03. So that would be like all of these numbers to 20. And that's 45 of my 51 pieces of data. And that is 88% of my data. So I can really stop here because that's pretty far away from 68% of your data. Now, it says approximately normal, so it might not be exactly 68%, but it should be close for it to be approximately normal. I would say 88% is nowhere near 68%. So I would say that this is not approximately normal, since 88% of data is within one standard deviation of mean, which is far from 68, 95, 99.7 rule. Okay, so I would say it's pretty safe to say that this is not approximately normal because that's pretty far away, which I agree with. When we looked at this, like, this does not look like a normal curve. It looks like it is skewed. Okay, so it's pretty safe to say, yeah, probably not approximately normal.